So let's continue our discussion of intramolecular forces and inter. We spent a lot of time today talking about one type of intramolecular attractive force, and this is called a chemical bond. And this is a covalent bond. All right, and as a reminder, the word co means that they're cohabitating, co-sharing these valence electrons. Don't forget the dots that we draw in these Lewis dot diagrams come from the valence electrons. I'm looking at my reference table to look for those valence outermost. For instance, I look at bromide. Okay, bromide has an outermost 7 in my chart. I know there's some other numbers there. It has electrons in 4 different energy levels, but I'm just looking at that outermost number is 7, and understand that we're going to be dealing with the octet rule. That octet rule means that for most elements beyond the second row, having 8 is an important stability factor. Now, when I say stability, I mean low energy. As I keep talking about, atoms want to become stable, low energy when they bond. Things in nature go from high energy to a dispersed form of energy that goes outward. Generally speaking, energy gets dispersed from high to low. So the way that atoms do that, they use each other. So if bromide here has 7 valence electrons and this one has 7 outermost electron, it's a nice fit to show how Br bonds with itself. Do not forget that this pair of electrons that's being shared, this cohabitating, okay, is really a bond. Okay, and sometimes you'll see it as a dash, and sometimes people will write the lone pairs of electrons, and sometimes they won't. Look at oxygen. Everyone knows it's O2, but now you know why. As we did in class, each oxygen has 6 valence electrons. So by sharing, each one of these oxygens feels like it has 8. Why is that important? Because each oxygen is, well, it was 2-6. It had 6 valence electrons. We don't care about the filled shell. It's that outermost valence shell that needs to be satisfied. And by sharing 2 more electrons, it can be that 8, that octet rule. If you look at your periodic table, gaining 2 more electrons, you become as stable as neon. We talked about those guys all the way to the right on the periodic table do not bond. Okay, they just sit there because they're stable. Okay, now we talked about nitrogen. Now nitrogen is 2-5. It has 5 valence. Notice the 5 dots for each. That means it needs to have that 8, 3 more, and that's why you have 3 bonds. And by sharing, hey, you can see each N has a total of 8. And if I was to draw this, we draw N triple bonded. This is an important form of nitrogen that we cannot utilize because of those triple bonds. It's too stable. It's too strongly bond for plants to use. So we have nitrogen fixing bacteria that break these bonds so that boom, 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 we can now break and utilize those nitrogen. But you should be able to figure out why nitrogen wants to make 3 bonds. Why oxygen wants to make 2 bonds, right? Oxygen's written with those 2. You should understand that H, party people, okay, wants to make 1 bond right there. 1 bond. That 1 dash is a bond. Okay, that's very important. If you look at carbon, carbon is 2-4 right in the bottom of your reference table. So it needs 4 more electrons to be shared with it. Therefore, 4 bonds. Okay, and I can draw it this way, carbon with 4 H's. That dash represents a pair. Now, the reason why I'm drawing it kind of spread out in 4 directions, these pairs of electrons that this dash represents kind of repels these guys into this structure where these electrons are equally far apart. Okay, we'll learn about VSEPR theory about that. But what I want to get into, since we've been talking so much about these intramolecular bonds, which is bonds, I want to get to attractive forces, okay? And I want us to also continue writing these Lewis dot diagrams, all right? So let's do that, all right? So let's talk about CO2 here, very important molecule that we're going to be talking about in cellular respiration and photosynthesis. So you should be able to draw this guy. So carbon starts with 4 valence electrons for the same reasoning we've been using. Oxygen, and I'm just changing colors because I can, has what? 6. So I start with the 6, and this is a way you would approach this. Always start with 1 bond. Okay, and I'm putting out all the valence electrons. Now we can see, if you count by sharing, this oxygen only feels like it has what? 7. And by sharing, this carbon only feels like it has 6, and this one feels like it has 7. So the octets have not been satisfied. This is 2-7 now, it kind of gains one. Carbon was 2-4, now it's 2-6, and this is 2-7, so it's not been satisfied. So what we're going to do here is we're going to remove one of these and put that one here, and we're going to move another one and put that here, and you can see this oxygen now feels like it has 8. Now it's got that octet. Now it's stable. This carbon, 2, 4, 6 is 2-7, so we're going to have to do the same thing on both sides, and you can see what's going on here. I'm going to move this guy over here, and I'm going to move one of these X's here, and boom. What do we have? Well, we have, lo and behold, we have oxygen feeling like it has its octet by sharing, and the same thing here. Octet is filled, 2, 4, 6, 8, and the carbon feels like it has 8. And if I redraw this, what do I have? I have carbon double bonded to the O, and in chemistry we would put the lone pairs out there. There's 2 lone pairs, you notice, and that's the proper way to do it, but I'm not after that today. Notice carbon doesn't have any extras. Now, CO2. Let's consider CO2. And I want to kind of move our discussion in terms of polar and nonpolar molecule. We just dealt with something called molecules here. The reason why they're molecules is because they actually have a finite number of atoms bonded so that every atom has its 8. So in CO2, you have 1 carbon and 2 oxygens bonding together to make this particle. Now, I drew it linear because there was no lone pairs to bend it that way, but you don't have to know that for this course. Okay, so having no lone pairs to bend the electrons one way, it'd be straight across. Again, you don't have to know that. But given this structure, you need to understand if this is a polar or nonpolar. Well, when we look at polar and nonpolar molecules, we have to consider how the electrons are being pulled. When I gave you the periodic table today, upper right-hand corner, over to the right and up to the right, excluding that last row of noble gases, helium, okay, neon, argon, okay, all the way coming down. These guys we don't include because they're noble. So the upper right-hand corner are the smallest atoms that track the electrons. Well, oxygen is the second most important, or strength, or we would say electronegative atom, meaning it's able to pull electrons away from it. So these pairs of electrons that I drew closer to the oxygen because oxygen is stronger, so it pulls those electrons away from the carbon. So the carbon kinda lost the electrons. So we would say that the carbon in the middle is probably a little bit positive, and the oxygens in the end are a little bit negative because they have the electron density. Again, if I was to draw this down here, there's more electrons, these are negative signs, on the ends than they are in the middle. So there's an unequal distribution of electrons, and this is what a polar molecule could be. A polar molecule means you have an unequal distribution. However, in the case of CO2, both sides are the same. Yeah, the inside is different, but you don't really get to see the inside. So both poles of the molecule, this could be the north pole if you'd like, the south pole, both are partially negative because they both have more electrons because they pull them that way. So because this has the same unequal distribution on both sides, we would call this molecule nonpolar. Yes, it has unequal distribution, but both sides are the same. So when you're looking for a nonpolar molecule, what an easy way to identify is to look for a symmetry. When you have symmetry, that means you're the same all the way around. And if you're the same all the way around, you're not going to have what? Different poles. To be polar means you have differences in electron density. Yes, we do have differences in the middle, but since the outside's the same on both sides, CO2 is nonpolar, and that's important. So let me just clean this up. Okay, now let's take a step back and look at CH4. Look at CH4, you say, oh, okay, two different atoms have two different electronegativities. That's a word I didn't talk about in class, but electronegativity is the ability to pull on the pair of electrons. And generally speaking, atoms that are smaller in group 2 are the ones that have the greatest attraction. I know hydrogen's smaller, but because carbon, nitrogen, oxygen have a greater number of protons, they're better pullers of electrons. So those group 2 elements that are the best pullers are the smallest ones. So carbon and hydrogen, actually carbon's better at pulling the electrons. You don't have to know this to do this. What you should know is that carbon and hydrogen have about the same attractive force or same electronegativity. So when you see a hydrocarbon, and a hydrocarbon is something with just carbons and hydrogens, we now know that carbon must make 4 bonds. So anytime you see a hydrocarbon, you know, no matter what the shape is, it's nonpolar because these electrons are equally interdispersed. Again, remember, every bond's a pair of electrons, so this would be a pair that's in between both. This would be in between both. So anytime we have hydrogens and carbons, we know the compound is nonpolar because there's no unequal distribution because carbon and hydrogen have the same attractive force. That's one you should know. The rest of ones are easy to identify based upon how what? Over to the right and up you are, excluding the noble gases, excluding helium, neon, argon. Okay? So methane, although you would say, wow, this maybe have some differences, because it's a carbon-hydrogen bond, okay, there really isn't any difference. There's no unequal distribution, so this is clearly a nonpolar molecule. Okay, let's go to number 6 below. So I'm going to draw the Lewis dot diagram of CHI3. That means I have a carbon. Now I know carbon makes 4 bonds, so I know that's going to be my central atom. And if you didn't know that, that's okay. It's not something I'm going to test you on. All right. And then of course I have an H, and I already know my H's have 1 bond because they only have 1 valence electron. So boom, they're done, and it's stable. Then I have I3. Now I look at iodine in my reference table. A lot of numbers, but the last number is 7. That's the one I care about. So I put in my 7 valence electrons, and you can see how nicely this fits. So I'd have 3 iodines, and each iodine brings 7 valence electrons, and carbon brings 1, and you can see the iodine, by sharing, it's 7 with the 1 from the carbon has the 8. So this works out nicely. Okay, so the question is this molecule polar? Or is it nonpolar? Well, if I look carefully, iodine and carbon are going to have 2 different electronegativities. I don't care if you know which one is going to have a higher. It doesn't matter. The idea is that iodine, okay, is different from carbon, and it's not the same all the way around because this is not symmetrical in the same all the way around. You can see with this eyeball here that this side of the molecule has got to be different than this side. Carbon and hydrogen have about the same. Iodine and carbon are going to be different than the attractive force here. So this is going to make this side of the molecule different than this side. So this is going to be a polar molecule. In another course, you should be able to look up these values, but it doesn't matter, okay? So in essence, iodine is actually more electronegative than carbon, so it pulls the electrons more this way. So believe it or not, the negative side of the molecule is the iodine, and this is the positive side. So this side of the molecule is the negative end. But it's easy to identify a polar molecule when you see asymmetrical behavior where there's differences, right? If there was an iodine here, what do you think it'd be? You're right. It would be nonpolar because it'd be the same all the way. So the key, my friends, in chemistry is you're looking for symmetry. If you see symmetry, you know it's nonpolar. And you know why? Because if it's the same all the way around, you can't have poles. Now, Mason, Mr. Grotsky, I still don't get what a polar, because you show me 2 nonpolar, but what's polar? Look, well, let's go to a polar molecule. Let's go NH3. N has 5 valence electrons. And you could draw this many ways. There's my 5. And then hydrogen brings 1 for reasons we should know now. And you can see that nitrogen feels like it has 8, each hydrogen has 2. Now, is this a polar molecule? Well, if you look careful enough, if I draw this molecule like this, okay, the N is on this side, and the N is more electronegative. So in truth, I should probably draw these pairs of electrons closer. N is, besides oxygen, the third most electronegative atom. So this N, because it's on the second row next to oxygen and fluorine, pulls in these electrons greatly. Do you have to quite know that? No. But I'm just telling you how this all works. Okay? So H kind of loses the electrons. So the H's, okay, in this molecule kind of have their electrons pulled away. All the electrons are clustered or being pulled toward the nitrogen end. So we would say that the negative end of the molecule is right here and the positive end is here. And when you have two different things, you have poles. Like if you think Mr. Grodsky's very polar personality, or he's dipolar, okay, that would mean that I come in crazy one day and then very calm the next day. So the question is, I don't do that. Okay, so this clearly has a region that's what? Negative, electron rich, and then we have an area where it's electron poor of the molecule. So the electron poor area is the pole, is the place that's negative, electron rich is the positive. But you didn't have to know who's electron rich and electron poor in this course. All you know is, hey, this is not symmetrical. It's not the same all the way around. If it's not the same all the way around, there's going to be an unequal distribution of electrons, and therefore it's polar. So because NH3 is not symmetrical, hey, it has to be polar, meaning it has to have negative ends and positive ends. If you don't know which one it is right now, that's okay. So if we go to number 10, let's clean up some stuff here. We do number 10 together. Now you may say, Mr. Grodsky, hydrocarbon, but if you don't see it, go C2, 2 carbons, and there's 2 H's. Now I know carbon makes 4 bonds. Well, there's only 2 on each side, so 1, 2, 3, 4. You probably can see what's going to happen here. 1, 2, 3, 4. The hydrogen's going to make a bond. Make this out of the way. And you probably can guess what's going to happen here. This carbon doesn't have 8 yet, so if you haven't seen it already, you can see that this is going to have to be a triple bond between the carbons. How do I know? Carbon must make how many bonds? 4 bonds for a total of 8 electrons. Each carbon feels like it has 8. So if I redraw this, I got a carbon triple bonded to another carbon bonded to an H. Okay, let's pretend these weren't carbon hydrogens, which we know what? We know what? We know that these guys have the same electronegativity, so these guys have equal distribution of electrons, so guess what? It's nonpolar. Or is this symmetrical? Is it symmetrical? Yes, it is. What if I was to change this to fluorines? What if these were big old F's? Now, yes, I'd have to draw the other lone pairs around, technically speaking. But if I had these F's at the end, which would pull the pairs more so than the hydrogen, it still would be very symmetrical, and no side would be different, and this would be non-polar. Okay? So to identify polar and non-polar, we look at whether molecules are the same molar rate. Can you guess if carbon tetrachloride is polar or non-polar? Yes, it's non-polar because you're going to have what? 4 chlorines if you don't see it. Same all the way around. Are they sharing unequally? Sure, but there's the unequal distribution is the same all the way around. Can you guess what this is? Well, this is a structural formula showing a C bonded to an H, bonded to an H, bonded to an H, bonded to an O. Is this the same all the way around? No. So it's going to have areas of electron richness and electron poorness. This is a polar molecule. Now these guys are unfair to look at this way because you have to know that water looks like this. 2 pairs of electrons here and the H's are here. You have to know the structure. But if I drew the structure, you can see that this is not the same all the way around. Water is going to have an electron-rich area where the oxygens pull in the electrons. And it's going to have some electron-deficient areas devoid of electrons, and we'll call those positives. And those positives make sense because, as we talked about in class, hydrogen is 1 over 1. So it has 1 proton and 1 electron. Well, if you pull the electron away, you're left with a proton. So it makes sense that this molecule has a negative side and a positive side. All right. So keeping with our understanding of what is nonpolar molecules always will be symmetrical. It should make sense. You should not be memorizing. If you're symmetrical, that means there's no what? Unequal distribution of electrons. You may have unequal sharing between the bond, but throughout the entire molecule, it's the same. If you're polar molecule, you are non-symmetrical, which meaning you're not the same all the way around, so you're going to have areas of richness and poorness or unequal distribution. So if we go through, okay, some of the R groups right now, we should be able to recognize which ones are polar and nonpolar. So let's start with this. These are just carbons and hydrogens in a structure. So this is just carbons and hydrogens. This is a polar and nonpolar R group. Ah, very good. That's a nonpolar. How about this one? You have some differences throughout the molecule. Yeah, this is asymmetrical. This is going to have an electron-rich area. This is a polar R group. Okay, what about L-lysine? You have some hydrocarbons here, but you've got this N at the end that makes it different. What would this be? Very good. That'd be polar. Okay, how about this bunch of hydrocarbons? Right? That's just carbons and hydrogens. Even though it probably doesn't look symmetrical, these are just carbons and hydrogens, and carbons and hydrogens have the same attraction or electronegativity, so this is nonpolar. How about this right here? Nonpolar. Good. How about here? We have carbons and carbons, but an O at the end. Very good. Polar. So this is different. This is not symmetrical. What about this? Okay, that's polar because it's different. There's something different given there. Okay, what about this? Very polar. Polar R groups. Another polar R group.
Have your attention, please.